So hi, I'm Steve Rostedt. I'm an open source engineer at VMware, and I also want to give a shout out to VMware for allowing me to spend time on their dime to give presentations like this. So thank you, VMware. Now, let's get right to the topic. I have a lot to talk about. So this talk is about tracing a Busybox environment. Well, what does that mean? Busybox environments usually mean that you have very limited resources. You have limited RAM, limited disk space, limited CPU usage. For those that are coming to the Embedded Fest, I'm hoping that you really do understand what limited resources mean. Well, Busybox is an application that's designed to be very small and does everything that you usually need for minimal resources to be able to have a shell and some commands. So basically, you'll be given a way to cat files, echo into files, or echo commands, change directories, give listing. And if you have Dropbear, which is another embedded system, you also have SSH, SSHD, and SCP to be able to get to the box, which is very useful. But you still need to debug a kernel. And if you're debugging a running kernel in embedded space, if you're using Linux, you may have a custom drivers, unique environment, something very specific for your needs. So what do you do when you need to, if there's an issue with the kernel, you need to debug it? As I mentioned, I said I had the Dropbear environment for SSHD. And then from the next thing I hear is what I have now is the configuration I used for the Linux kernel. So when I went to the Linux kernel, went to when you build it, you have to set up options in your build environment. You would do this make the architecture that you're doing. Right now I'm doing ARM64. Menu config shows me all the configurations that I can do for the Linux kernel. And you can see here, if you go to the option of kernel hacking and click on that, and then you have an option that you click on tracers, it brings you to this menu. This menu shows all the tracing utilities that I usually will use. Some of these things will add a little bit more memory, require more memory to use, so you may not want them all, but I'm also going to share this screen and share this presentation, so I'm not going to talk about each one of these. You'll be able to see them, and then there's help menus as well to know what's going on. So when you go into the Busybox environment, I SSH into my virtual machine, and right here I see that there's a etc fs tab that the drop or build root environment created for me. And this shows you where all the file systems that it mounts on boot. And if you look in here, you'll see it has the proc file system, sysfs file system, temp and dev file systems. These are all pseudo file systems, which means that they're not actually attached to a hard drive. They're actually created virtually inside the kernel, and it's a way to get information from the kernel as well as to change the kernel at runtime aspects. But we want the tracefs file system, so I added this line that gives me access to the tracefs file system. And if you have the tracefs file system compiled inside the kernel, the sysfs directory will create this special directory called syskernel tracing that you can mount the tracefs directory to. So you don't have to worry about creating this directory. As long as you have the sysfs file system enabled in your kernel, this directory will automatically exist if sysfs is mounted. If you don't want to add this to your fstab file and you want to do it manually, you could just use this mount command and install it at that runtime, so you don't at boot up it won't be mounted. But then how do you access how do you modify or enable all the tracing within the Linux kernel? And to do so, you use cd to that tracefs directory that you mounted, and you do ls and look at all the files. These are command files that allow you to extract information and control the tracing utility within Linux. The ftrace tracing is all controlled through these files, this file system. Quite overwhelming, and there's a lot of files here. I've given lots of talks that describe a lot of this, so today we're not going to talk about it. We don't have time, especially now that we've had all these issues. But these are some of the main files that you really want to care about, so not all of them are important for you. And there's even a README file there. That README is actually an API, which means that you could use the README file that discuss everything that, or most of the options in this directory. And when something's not compiled in, it won't be there. So if you want to see if a certain feature is enabled or not, the README file, lots of times you could use that to determine whether or not a feature is compiled inside the running kernel you have. Now, one of the things that we look at is tracers. Now, tracers are a special type of tracing that actually do some modification of the system. It changes the environment a little bit to extract some special information. The two files for tracing is available tracers, which shows you what tracers are compiled into the kernel, and current tracer is how you enable or disable tracing, these tracers.
So if I were to look inside that available tracers with the cat command, again, everything's here is Busybox, and I see a bunch of tracers. Now, the first three you see there, the timer lat, OS noise, hardware lat latency tracer, they actually look for disturbance that the Linux kernel or the hardware will give to your system, and you'll be able to use that. So when you enable one of these tracers, it will actually kick off some threads that's going to do some work. So when the tracer is running, it actually will disturb the system itself. The tracer itself will disturb it, but it's actually doing so to be able to log and tell you what is wrong. I'm not going to talk about these. There's other talks out there that explain these tracers. One of the things that is very important that everyone likes to use is the function tracer, and you'll see it up there. The function tracer actually will trace all functions in the kernel. And when you enable this, it will just enable the functions. You can limit it, and I'll talk about that later. And when you want to see what's being traced, you cat the trace file. So if you look at the trace file, and there you'll see all the functions there that have been traced. If you want to disable this, there's that no-op tracer at the end there. That's a special no-op. That actually, when you pass in the no-op tracer, the NOP there, into the current tracer, echo that into the current tracer, it will disable all tracing. Now, also notice that these two numbers here, it tells you the entries that are in the buffer as well as the entries that were written to the buffer. That means that if the number of entries that are written to the buffer is bigger than the entries that are in the buffer, that means you lost some entries. That's because there's only a limited size for the ring buffer within the kernel. And for here, you can see 102,000 events are in the kernel, but 400,000 events were written, which means that 300,000 events were lost. The ring buffer inside the kernel by default is a overwrite ring buffer, which means that newest events will always overwrite the older events. So when you're looking at it, if something happens and you want to trace what happened at a certain thing, a certain instance or a certain issue that's happening. So when the issue triggers, you stop tracing, you'll see all the events that led up to the that issue, and then you don't worry about lost events. So if a normal producer-consumer type of tracer, where when the ring buffer fills and waits for the producer to catch up, you could lose events that actually came up to the incident or the incident that you want to trace. But this is an overwrite mode, so you actually should have all the events. There is an option that you could turn to make it into producer consumer mode, but that'll be talked about later too. Another thing besides tracer is what we have are events. If you look in the events directory, that is static points within the kernel that kernel developers think are important to extract information out. Again, the kernel is basically a black box. So when you're debugging a kernel, sometimes you want to have ways of extracting information to know what's happening within the kernel. Events give you that information, but they're static events and they're compiled. There's thousands of them within the kernel, and they're also grouped up. They're all associated in groups. So you have scheduling events, interrupt events, and whatnot. So they're groups, so it's easier to organize and enable them and disable them here, which you'll see in the near future. So for example, I'm looking at the sched switch event. The sched switch event looks at when one task schedules off the CPU and another task schedules back on. This is very, one of the crucial aspects of the kernel is scheduling tasks to see what's running, because if you're worrying about your system performing properly, you want your application to run properly and not being waiting for something. This allows you to see that. So here, the sched switch event is within the scheduling group, the sched system group that you see there. And if you look in the directory, there's the events directory with a sched group directory, a bunch of group directories, followed by a bunch of event directories, and a special file called enable. You echo one into the enable of that file, and suddenly your tracing is happening. Again, Busybox environment, cat trace, you see all that. If you zoom in a little bit, you'll see the sched switch. And if I look at this, you see the RCU preempt task, that's a kernel thread, that's scheduled out to the swapper task, which is basically the idle task. So nothing's really running. This is just an example of something I just did. And here you see it shows you the previous processes, the process ID, the priority of the task, and the state that it's scheduled out of. Right here, I is the same type of state that you would see in a PS command. Now, it's important to note that within the kernel, priority is actually inverse. That means that the lower the number, the higher the priority. The highest priority task in the kernel is priority 0. So when you see 120, that might say, wow, that's a high priority task. Actually, it's very low priority task. 120 is the default for normal, nice applications, normal applications. So now, if you're in a Busybox environment and you might be typing a lot of commands, and remembering what these commands are could be kind of grueling, it's good you could write scripts if you want. So what I did here is show you an example of just doing echo. It's something I actually did on the command line on my virtual machine. I echoed this information to have a way of just initializing the trace. All I want to do is clear out the trace and disable tracing so I could do stuff and then enable tracing. The first thing is there's a special file called tracing on to enable or turn on or off the writing to the ring buffer. And that trace file that I was catting, if you write anything to that trace file, it clears the buffer, erases everything in it. So this basically just stops tracing and clears the buffer. Then I say if I want to trace a specific task, so how would I do this? So the second one is I had created this do trace task command, and what I do here is I set the tracing dir. I go there. There's two special files. There's set event PID and set ftrace PID. The set event PID will say only trace tasks of this that for process IDs or task IDs, they're thread IDs basically, that are in this file. You can add as many as you want in there. Same for the set ftrace PID, which is for the function tracer. So the ftrace PID only affects the function tracer. The event PID affects all events, but does not affect the function tracer. Some people get confused by that. Then I enable tracing, and from here, if you notice, I do an exec of the command line. So this is a way to basically trace only a specific task or application you want. So you call this script do trace task, pass in, then you follow by your command that you want to trace. And what this will do is it will set all the tracing up, set the process ID for that task in these set event PID and set ftrace PID, and then exec it. Remember, exec doesn't do a fork. Exec just changes the process ID to run one application to another application. Now this new application you're running is now being traced. So don't forget to make sure that these files are executable. Then here's a little example for, I just wanted to trace function. I just want to trace the ls command. So do my init, I echo function into the current tracer, and I do my do trace task ls. And if I cat the trace, I look over there and I say, wow, there's 15,000 events in there, and here's what that trace did. Again, because there's 15,000 events, you'll see that the buffer's in matches the buffer out, which means that I lost no events. This actually has all the events that happened, all the functions that ran, the tracer, the ls command did inside the kernel was trace, and I got them all. Now, so let's say if I want to trace the children of these tasks. Now, the children of the tasks, what I do is I could echo a special echo one into a special file. For here is in the options directory. The options directory contains ways to modify the tracing, and one of the files there, commands that you could do is event fork. There's actually a function fork as well, but I'm not going to talk about that. That's for the ftrace, same thing. But for now, let's focus on the event fork. Event fork means that whenever a task forks and creates a child process, and if that process that did the fork, its process ID or task ID is in the set event process ID file, that means that its child will also be added automatically. You don't have to do anything. So the children will then automatically become traced as well. So let's say I want to take a look at tracing the parent of the shell script that I'm using. So I grab the parent process ID from my shell script. The $$ means the process ID of the shell script, and I get 182. So I set event PID to 182, and just to see what's going on, I init trace. I enable all system calls. This is kind of like strace, but it's from the kernel side, and it traces everything, not just one task. Although right now, because I set the set event PID, it's only going to trace one task, but I could trace all system calls from every task if I wanted to. But here I only care about the 182 task. And when I look at this, now the system's idle, and I noticed that the parent is doing a lot of stuff. And this kind of surprised me, like, oh, the parent's doing some sort of polling. If I look into the next page, it's doing a lot more polling. I'm like, okay, maybe I don't want to trace my parent of the shell script. Let's trace the parent of the parent. So when I got to 182, I searched the parent of 182, and I got 163. Now this is the main Dropbear application. So when I SSH in, this guy is going to fork and do something. So I do want to trace this one. So from here, I echo 163 to my set event PID, enable tracing, and then I cat trace and see it's doing nothing. It's just waiting for a new connection. Great, because now I want to trace my SSH connections. So what I do is I SSH in again, and then I cat trace, and there I actually see all the system calls that are being done by the Dropbear. And if I look in here, you can follow through, walk through the tasks. I notice that, well, this is task 303, which actually is the fork. So the 163 forked to 303, and then this guy's forking another process here. The fork call actually uses the sysclone system call. And you'll notice here the return of it as well. Every system call gets two events: an entry into the system call and an exit the system call. The entry of the system call shows the parameters that are being passed in, and the exit shows the return value. The return value here is a hex value of 130. If you converted that to decimal, it's 304. If you look down, there is my 304 shell script. So, by the way, if you want to clear this, like I said, writing scripts in Busybox is useful if you're doing a lot of tracing. So here, I disabled tracing, I cleared the trace event, I cleared all the events. Now, if I echo 0 into the events enable file, that will clear all events in all the groups and all the events as well. If I echo 1, it enables all the events in all the groups. And same thing for systems. If I echo 1 in the sched switch, and as I did in the system calls, that enabled all the system calls. So you could enable groups, individual events, and all events, and also disable them like that the same way. So now the and also I cleared out the PIDs for both the set event PID and set ftrace PID. And yes, there's a no trace PID, which is the inverse, where any process ID that's in here will not be traced. And then I created the reset file and made sure it's executable. So here I cd to my tracing, I reset everything, I enabled the event forks file, and then I echo 163. And from here, I want to see, I'm just interested in the system clone, which was I know that that's what fork uses in the Dropbear uses to fork, is the sys clone. So I'm going to keep those trace events. Now, if you'll notice in the event, it was just called sys clone, but the events themselves, since they're actually split into two, the actual events names are sys enter clone and sys exit clone. That's something you have to just remember. It's special for the system call events. And then here, I'm also going to trace the exec when sysclone exec something. And for kicks, I'm going to also trace the scheduling event for when something wakes up one of these processes. Now, the set event PID is smart enough to know that if it doesn't care about who woke something up, but if on wake up event, if the process that's being woken up, even though the waker's not may not be in the set event PID list, if the process that's being woken up is in the set event PID list, it will trace that event. So you could see when one of those events that are in the set event, or one of the tasks that are in the set event PID list is woken up. You get those events, they're not lost, and you don't have to worry about it. Then I enable tracing, SSH in, and go look in here, and here's the trace that I get from the parent child. You'll notice that there's my 163 that enabled, or the Dropbear, it was woken up. It did a fork, and it cloned 155, which translates into decimal to a 341. So you can see it forks itself, and then it does another fork to create the shell. And then this shell actually did something strange. I didn't actually look deeper into it, but it called this ID guy here. So it actually forked again and created this ID process. Now I want to go back and look at this this kind of like this cryptic line, that a third column there that you see lots of letters and dots and stuff, and like say, what is this? I'm going to spend a little time explaining that just so you know, because it is kind of important, especially in embedded device and embedded development, and especially if you're interested in real time. So in the top header of that file, you'll see that it actually gives you information of what each of these fields are. The first one is whether or not interrupts are enabled or disabled. If they're right here, you'll see it's interrupts are disabled, which means that no interrupts are going to come in, which means it's not going to schedule out, and no interrupts will not happen. So if you're worried about interrupt latencies when interrupts actually come in, this is a very crucial field to be aware of. The next one is the need resched field. This means that a task is woken up that wants to schedule in, but it has to wait until interrupts are enabled, as well as the preemption count is ready to do. So if it has to wait until the CPU is ready to schedule before it can schedule in, and while it's waiting, the end flag set, so you can actually see the time of various of events saying, oh, something wants to schedule in, but can't do because the system isn't letting it to. Very important. The next one is whether or not you're in interrupt, what type of interrupt context you're in. Are you in normal? If it's just normal processing, it's just a dot. But if it's a small h, it means it's interrupt context, hardware interrupt context. If it's a small s, it means that's in soft interrupt context. If it's a big H, it means that it was a soft interrupt context that got interrupted by a hard interrupt context. And finally, there's the preempt count that tells you that when that's anything other than a dot, that means that the system cannot schedule out. Interrupts can happen, but it cannot schedule. And the last one is migrate disable. I'm not going to talk about that right now. That is for real-time tasks, or for real-time development. Now, one of the things I noticed is this repeat in my trace is the Dropbear process got woken up 4 times. I'm like, why? So let's go and investigate that. So I set up everything like normal, but this time I'm going to do a stack trace on this wake up event. So what I do is I do a stack trace trigger. Now, so here's the stack trace. So hopefully I don't remember exactly what I told you about the triggering of the stack trace. I got to the functions here, and what I want to look at was with the stack trace of the function. So hopefully I'm just going to go back. I don't know if you guys repeated this or not, but I'm going to continue my talk. Anyway, what fun we're having here. And so when I looked at the stack trace of why these events actually happened, I see this whole full stack trace. Now the stack trace shows the list of everything that happened. It gets recorded into the ring buffer. And from here, notice that there's two functions I want to trace or look at. There's a pull wake and the TCP v4 receive function, which happens to be the first function that is triggered when TCP TCP functionality inside the kernel is executed. So when this is hit, I know a new packet came in. So the question is, because there are four identical stack traces, I don't know if it's just a loop happening in the beginning of the stack trace, or actually this full path went through 4 different times. So I'm going to look at these two functions, and I'm going to add them to the function tracer. So by doing that, I use the set ftrace filter to only trace these functions. It's not going to trace anything else. It's going to trace these functions, and I'm going to echo the function into the current tracer, so enabling the function tracer along with events. So I turn tracing on, and from here, actually, with the wake up events going on here, I see that the Dropbear executed application is woken up 4 times. But I also see at the same time that the TCP v4 receive function and pull wake were called 4 times as well. So that means that there was 4 packets that came in. It wasn't some special loop that just happened to wake up this guy 4 times. It actually was 4 different packets that came in that the TCP v4, that the Dropbear application had to be woken up to look at it. So it's not a bug. It's normal normal process of execution. So finally, let's also look at, for more information, let's look at what's being opened. So if I look at opening, I turn it on, and I'm looking at the open system call of Dropbear. And here I can actually see all the system calls or everything that it opened. But unfortunately, the file name inside the kernel, all I see is a hex number. I actually don't see the file. And that hex number is actually a user space address, not even a kernel space address. It's a user space address. So all I have is some number. They're all different. So it's opening something different each time. That's the only thing I basically know about. So how can I handle this? Well, by eProbes. Event probes have just been added to the 5.15 kernel, which has just been released. So it's in mainline right now. Recent kernel is the event probes. And this way you can add a probe on top of an event itself and extract its fields. And then you can modify existing events, basically. So basically you create an event. So you can basically make one event look different now with a new event. And it reads pointers just like kprobes does. And that means that you could follow a pointer, you could actually follow the structures and get data that the pointer references. Now, here's an example of how to execute event probe. Remember, this is Busybox. All I have is echo, cat, and all that. So I echo this command. So I do the eProbe. I create my new event called Exec. I'm going to attach to the syscall sysenter exec ve event. And I'm going to have my create a field called prog. And I'm going to make it look at the file name field of the exec v system call event. And by putting the $sign there, that tells the command that this is a field of the event that I want to use. And if you see that +0 parentheses colon uString, that means I want to dereference that pointer. So the file name is a pointer. I'm going to dereference that pointer, and also I'm going to convert it into a user space string. Now it's important to say :uString and not just :string. :string means that it's a kernel space string. Here it's a user space string, and the kernel knows the difference. So if you say string here and it tries to access user space memory, it's going to give you a fault. And it's not going to fault the system. It's not going to crash. All it will do is it'll print out fault in your trace. I do the same thing for the open file. And then I enable all the normal system calls, but I also enable my special events in the event probes group. So I enable exec and open, do the tracing on, SSH in, and here, now the file names, you'll see a list of all the files that it's open. It's not just the hard-coded hex. I actually see the files that the program is opening. And I also, for the exec, when the exec happened, I see it's exec /bin/sh. I see exec the /user bin ID. So I could watch what's happening. I could see inside the kernel, from the kernel, I could see inside user space. But there's a funny thing. In my trace, I noticed this here. It said file equals fault. That means that it tried to access memory and it wasn't available at the time. So it doesn't crash the system. All it does is it inserts fault in your trace. Now, why did this fault? I mean, it's not a bad address. So let's look into this. Why did this happen? It's because trace events have to be atomic. It's because when a trace event happens, it happens in any context. You know, it could have interrupts off, preempt off. It can't schedule in. So it has to be, whatever it does, it has to be very small in return. So it can't schedule out. User space code, though, can not exist. I mean, sometimes it's on-demand processing. So when you actually have some data that you access in user space, it's not actually loaded into memory until you access that data. That's when the kernel will then load it in. Why load, like start up Firefox and load everything into memory when you only going to use a small portions of it? So everything's on-demand loading. So if a string has not been referenced before, it's only referenced within the system call, it's not going to be loaded until the system call actually references it. So here's an example. I wrote this little program to test my theory, and when I ran this, this file will always fault. Reason being is because I made the file pointer point to a constant variable that's located in a different aspect of the executable. So when the first time it's actually references inside the open system call. So when it goes here open, it calls file, on entry of the system call, that file, that information, that etc password is not in memory yet. So if I try to trace it, it's going to say it's not there, I don't know what it is, and faults inside the system call, and then it won't be available until exiting of the system call. So how do we handle this? That thing about exiting system call, knowing that it's available. There's this thing called synthetic events that's been introduced a while ago for 17 kernel, and it's allowed to connect two different events into one. And that means you can make a single event access event fields of both events. Now, because it needs to access the fields of the second event, the synthetic event doesn't get triggered until the second event happens. Actually, after the second event happens. So you can also show time delta between those two events, which is very useful as well. So how does synthetic events work? So first thing you do is you create the synthetic event. Here I create a synthetic event called myopen. I'm going to create two fields, file name and return. The first one's going to be a U64. This is, like I said, 64-bit machine. So I know that pointers are 64 bits. So I'm going to say U64 address and assign 64-bit for the return value. And then I create a new trigger on the enter of the event. So remember, the open at has two trace points. So one's enter and one's exit. So on the enter, I'm going to create a trigger for the histogram. I'm going to create the keys for common PID and then file name. And then I create another histogram trigger onto the exit open at. The keys have to match. So it doesn't have to match actually the field names, but the values have to match. So basically I'm saying when the common PID, which is the task that triggers executes the trace event of the sys enter open, matches the process ID of the event that, or the task that triggers the sys exit open, it will actually trigger this synthetic or trigger this command. That's where you see the on match up there. On match tells you which I'm trying to match. Now the keys could be different fields as long as the values match. And then I pass in information to pass the file name in. So I'm actually, you notice I set a variable file equals file name. So I'm going to take the field of the file name, put it into a variable called file. And on the exit side, I'm going to put that into another variable. So I'm moving one variable into a second variable. The reason why I'm doing that is because at the end, you'll see I'm going to execute the synthetic event. I'm passing in file names. It only has access to variables for that histogram trigger. So it can't access the variables from the previous histogram trigger. So it's best to just copy the variables that you want to pass to the event over. And then I create my synthetic event to attach it. So now I'm going to look at the file name of I'm going to create my event probe to attach to the synthetic event. So now I have access to be able to look at the file name address of the synthetic event, not when it enters the system call, but when it exits the system call, I get the address then, and then that's when I'm going to do the conversion. And then I enable all the events. I enable the event probes, and then I enable tracing. Notice I didn't have to enable the synthetic event because the event probe will be triggered whether or not the synthetic event is enabled or not. So I don't even have to worry about the synthetic event. And then if I go look in here, I see all the events, and also notice that it's one single line. Not only do I have the file that is being opened, I also get the file descriptor that returned from it. Because remember, this is on the exit of the system event, so I have access to the information of when it entered the system call, and I have information when it exits the system call. And here I put both those informations into a single event. And then here is that file that actually faulted. And if I go back and look at the original code, you'll notice here's the file. Now, how do I know it's faulted? If I go back quickly, you'll see that TTY is there twice. Well, if you look at it, that TTY is there below it, and it has the same address of the one that faulted. So that means that the first time that that string, the dev tty, was actually accessed was in the first system call for opening, and that's why the fault happened. But it came back out, and then it called it open again on the same string, and when that open happened, it was already in memory, so the trace was able to trace it. Just happened to be so. So anyway, this is too complex to do. Okay, this is very hard and complex, and it's kind of hard to memorize. So what can we do for Busybox environments? Well, we can still use Userspace on our host. So with libtraceevent or libtracefs, which is a library, a Userspace library that's going to, the 1.3 is going to be released soon. It's already in there. You can download it from this website, the development branch. But when it's finally released, it's going to give you this thing called SQLHIS. It's an application. It actually comes from the man page for one of the API, tracefs API with tracefs SQL. Man page will give you this application that's very useful. But it requires access to the tracefs file system to be able to do these conversions, and you'll see this. But we're in a Busybox environment, and the whole point of this talk is the fact that I don't have to install anything else except for Busybox. So, but the SQLHIS could read a directory not just from the host system, but you can actually redirect it to read the directory from something else. So you can actually copy over the event directory from your board over to your host and actually execute these commands, or the simple commands, to get the new commands that you need to do, the echo commands. So for example, here, SQLHIS comes from the name, it's SQL. Basically, it does a select. The first thing is I'm going to create a new event, my synthetic event called myOpen. I'm going to select, I'm going to do start.filename as file. So I'm going to create a table, basically. Think of events as tables. So every event field is a column, every instance is a row. And I'm going to join two tables, the start event and the end event. So I'm going to say start.filename from the first event as file, and I want the end event, the return value, as FD. I know it's a file descriptor, so I'm going to say it's a FD. Then also here I added doing the time delta, and then you have the from event. So I say from event from the sys enter open as start, because once I do that as start and define the event as start, I can use start throughout the whole calculation. That's why in the beginning that start.filename is the same as sys enter open.filename. And then I says join, so I'm going to join the two tables of the sys exit open as end. Again, I'm going to alias that sys exit open as end, so I could use end as the in replace of the name throughout the whole command. And then on start.commentPID equals end.commentPID. This is where I'm going to say these two fields have to match to do the join. Just like you'll see that this is where the keys come in. And when you hit enter, it shows you the information that you need to do, the commands that you actually have to type. So you could cut and paste this and just put it straight into your Busybox board, and there you have it executed. So again, it shows you even the deltas here, and I'll talk a little bit about that later. And now getting tracefs directory to your host. Well, you could use your host tracefs file system because most of the time the events are the same. If the events are the same, fine. But what happens if you have a custom board and you have custom events that are not on your host? You need to get this the event directory over from your board onto your host. So maybe you could, maybe you could just copy them. You'll use SCP, copy them over, or you could use this tar trick where you SSH in and then you tar the factory there. By the way, only copy over the events directory. Don't copy over the actual tracing directory, because the tracing directory has some files that will just give you data like dev0 will. So you only want so you need to create the tracing directory, but then you only add the events directory. But you can't do this. Why? Well, that's because the Busybox and Dropbear copy has this way of always checking to see the size of the file before it copies it. And unfortunately, all virtual file system files have 0 size, whether or not. If you go and do an ls -long, that means that stat on these files will give you a 0 size, and that means when you copy over, all these files are going to be empty and useless for the parsing. But copy works. So if you have enough disk space on your, or like storage, to be able to copy the event directory someplace else, or NFS mounted or something, and copy it, copy just does the copy. It doesn't actually care about the size. That's good. That works. But what happens if you don't have the storage? Now, I don't have time, and I've been wasting up by this presentation is going to be available. So this actually is a workaround hack. And I was playing with different ways, and I found out that if I do a find of the events and execute it and inject, ASCII, or basically ASCII of 0, 1, actually 0, 1 character and a 2 character and wrap it around the name and then cat the file. So basically, and then I type it or SSH to my host machine that runs a full Perl script that reparses it and then creates the directories and creates extracts it. Basically, what this is doing is this is a hack homegrown tar command, basically what I did. But it's there, have fun. This actually works. And what can you do? So on your host machine, you can actually put -t/temp/tracing of your code, execute it, and it will give you the full command that you need. And then you could cut and paste this into your onto your board, hopefully whatever you do. And then I CD'd in and just to make it smaller on the screen. And then I typed in my what's it called? My event probe to attach to the synthetic event to add the file name with the time delta on it. This I'm like, ooh, we have time delta in here. Let me add the time delta there. And then I enabled my open event, and then I just let it run and execute. And there I have, and here's just letting it run. There's my shell script to open this stuff, and it gives you the how long that function happened in microseconds. By the way, if remember it said timestamp _usex. If I left off the _usex, this would be nanoseconds. But that's usually too much precision that I want. I only care about microseconds. So the first open that it did of the password took 355 microseconds. Second one took 500 of the history file, took 531 microseconds, and it also traced the cat of the trace file that's right here. And the reason why it has ... because it hasn't gotten the name of it yet. It took 18 milliseconds to read this file.